Hello children, welcome to Deeksha Online. It is crash course and today we are discussing work, energy and power. First, let us take up the discussion of synopsis based on this chapter. The basic idea of this chapter is all about the idea of work done, the idea of energy and the idea of power. There are some additional concepts as well, like we will be borrowing the concept of momentum conservation, and we will apply them to collisions as well. Let's take up each one of these details. You know that work is said to be done if the application of force or a point of application of the force produces displacement. For example, an object experiences a force and assume that it undergoes a displacement. We say work is done. Work is said to be done if the point of application of the force undergoes a displacement. Quantitatively speaking, how to calculate the work done? To calculate the work done, we consider two cases. One is if the force is constant. If it is a constant force, the work done by that constant force is given by F dot S, or this is Fs cos theta, where F is the force, S is the displacement and theta is the angle between them. For example, we can consider this case. Let's assume that this is the direction of force and this is the direction of displacement. Then theta is the angle between them. Or we can also consider this case. Let's assume that force is along this direction while the displacement happens along this direction. So if the force is constant, work done is given by F dot S, that is Fs cos theta, theta being the angle between force vector and displacement vector. But what if this is a variable force? The force under consideration is variable. If the force under consideration is variable, then what we do is something like this. Let's assume that this force keeps varying, and during this process, we'll consider a small displacement, say ds, over which I assume the force to be constant. And I calculate the work done over that small part given by F dot ds. And the net work done is integral dw, which is integral F dot ds. So, work done by a variable force is given by integral F dot ds, where F is the force, which is a function of distance or time, etc. And the net work done is integral of this particular term. This can also be calculated graphically like this. To calculate it graphically, we draw a graph of force versus displacement. For example, this is force and this is displacement. And if the force is constant and the displacement is from S1 to S2, then the area below the curve. So we calculate this area and the area below the curve gives us the work done. So work done is equal to area below the curve. And of course, this is on displacement axis. Same thing can be used even when the force is varying. For example, let us consider a variable force, and this is F versus S graph. If I assume that force is varying, then we can calculate the area bound by this curve, and the area gives us the work done. The total area gives us the work done. So graphically, you can calculate the work done simply by calculation of area below the curve. This work done is a scalar quantity. However, its value can be positive, negative, or it can be zero. For example, the work done is positive in the following case. Let's assume that there is a block which is displaced by a force like this. So notice that in this case theta is less than 90 and the work done is positive. Or if I consider an object which is falling under gravity, the object is falling under gravity and the displacement is in the downward direction. So work done by gravity is positive because both of them are along the same direction. So work done is positive in this case. Work done is negative in the following cases. Suppose I consider a block. Let's assume that there is a force along this direction and the eventual displacement happens along this direction, and theta is the angle between them, and theta is of course more than 90 here and of course less than 180. So in this case the work done by the force is negative. Or we can consider one more example. Let's assume that an object is being raised along this direction by applying a force. Now the gravity is trying to pull it down, so work done by gravity is negative as gravitational force is downwards while the displacement is in the upward direction. Work done is 0, probably under several cases. One is possibly force is 0, or displacement is 0, or theta is equal to 90 degree. Maybe the force is 0, or displacement is 0, or the angle between them is 90 degree. For example, an object under the influence of no force, obviously no work done. Displacement is 0. Okay, there is a heavy block, you are trying to push it, but the block does not undergo any displacement, work done is 0. Or if you consider the case of a uniform circular motion, the force is acting along this direction, the force is acting along this direction, centripetal force, and the instantaneous displacement is perpendicular to it. So clearly work done in this case is 0. Or you can also consider one more case. Let's assume that there is a porter carrying a load on his head and he is moving along this direction. Work done by gravity is 0 because gravity and displacement are perpendicular to each other. So you can consider any of these examples to prove that work done is 0, work done is equal to 0. Any of these ideas can be used. Here, couple of important points which should be kept in mind. Suppose I consider work done by a conservative force. In the case of conservative force, over a closed path, the net work done is equal to 0. It does not depend on the path also. It is work done is independent of the path chosen. It is independent of the path chosen. For example, central forces, spring forces, gravity, etc. are conservative forces. Remember, when only a conservative force acts within a system, the kinetic energy and potential energy can change into each other. But the total does not change, the total remains constant. So in such cases, work done is completely recoverable. You can recover the entire work done. In the case of non-conservative force, over a closed path, net work done is not 0 and the work done depends on the path chosen. So work done depends on the path chosen. You know that SI unit of work is joule, represented by uppercase J, and a couple of important conversions which should be kept in mind are 1 joule is equal to 10 to the power of 7 erg. 1 joule is equal to 10 to the power of 7 erg, one of the very important conversion factors. and 1 erg therefore is 10 to the power of minus 7 joules. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules, and 1 joule is equal to 6.25 into 10 to the power of 18 electron volts. And in terms of million electron volt, 1 million electron volt is equal to 1.6 into 10 to the power of minus 13 joules, and 1 joule is equal to 6.25 into 10 to the power of 12 million electron volt, and 1 kilowatt hour is equal to 3.6 into 10 to the power of 6 joules. Remember these important conversion factors. They are going to be quite useful as far as your problem solving is concerned. The idea of kinetic energy. Idea of kinetic energy. Kinetic energy is the energy possessed by a body by virtue of its motion. So it is the motion which is responsible for kinetic energy. And this kinetic energy is given by, as you all know, half mv square. Half mv square. Many times it is written like this: kinetic energy is half m. This is basically v dot v. Just keep in mind, you can also write it in the form v dot v. Also remember, kinetic energy is frame dependent quantity. It is frame dependent. It is a frame dependent quantity. So remember this important idea. Kinetic energy is always positive. Kinetic energy is always positive, and it is a scalar quantity. It's a scalar quantity. It depends, as I said, it depends on the reference frame. And kinetic energy and momentum are always associated with a moving body. For example, if I consider kinetic energy, which is given by half mv square, you know this can be written as mv whole square divided by 2m or p square divided by 2m. So I can write kinetic energy is equal to p square divided by 2m, or p is equal to root of 2m into kinetic energy. Remember this conversion factor, one of the very important conversion factors. Remember this. Potential energy is the energy possessed by an object by virtue of its configuration or position in a conservative force. So this is by virtue of its position or configuration in a conservative field. Conservative force field. Remember, potential energy is a relative quantity. By taking some reference as 0, we calculate this potential energy. Remember, it is defined only for a conservative field. Now, how to write that potential energy? So, potential energy is nothing but the negative of the work done by the conservative force. The change in potential energy, is nothing but negative of the work done by the conservative force. So, negative of the work done by the conservative force represents the change in potential energy. So, this can also be written like this. This is equal to UB, that is delta U is equal to final potential energy minus initial potential energy minus integral f dx divided by I to f. This is how you write the change in potential energy. We can also relate potential energy and conservative force through the following equation. This is given by the following equation. The conservative force is equal to minus dou u by dou x I cap minus dou u by dou y j cap minus dou u by dou z k cap. This is many a times written as minus del u, or known as minus grad u, gradient of u. However, if the force varies only along x direction, it's a function of x, then we can write f is equal to minus du by dx, or u can be written as minus integral f dx. That is what I said at the beginning. Potential energy or change in potential energy is given by this expression, or potential energy I can take it to be infinity, because at infinity the initial potential energy can be treated as 0. So work done to bring, or say to assemble the system from infinite separation to the separation given. Well, remember, if the force between any two objects is attractive, potential energy is negative. If the force is repulsive, potential energy is positive. One of the important things to be kept in mind is, if the force is repulsive, potential energy is positive. If the force is attractive, potential energy is negative. This potential energy is actually related to the idea of equilibrium also. Let us see how to write this. This is understood in terms of potential energy curve. Suppose we draw a graph of potential energy versus, say, position. This is potential energy versus position. Let's assume that a graph is drawn like this. Let's consider this is the graph. Now, let us consider a couple of points for our discussion. This is point A, this is point B, and this is point C, and here is another point D, and here is one more point E, and I got another point, say G. I'm not using F here. F is used to represent force. Now, so notice that here, etc., the potential energies are different. Now, just remember that F is equal to minus du divided by dx. That's right, F is minus du by dx. Now, if I consider the slope, your du by dx gives you the slope. That's right. So, at A, the slope is 0, at B, the slope is 0. So, force at A and force at B are equal to 0 each. Force at A is 0, force at B is also 0. While the force is not 0 at the remaining points like C, D, E, G, etc. So, at those points the force is not 0. Now, let us analyze these positions. If I consider A, at A, the potential energy is least and the force is 0, and this is what is called as stable equilibrium position. At A, it is stable equilibrium position, as this corresponds to 0 force, and at that position the potential energy is minimum, and in fact the second derivative of the potential energy is positive. And if I consider C, at C, what about C? If you look at C, du by dx is negative, so F is positive. If F is positive, what is our conclusion? The force between the particles is repulsive. It is repulsive, right? Likewise, let us consider some other positions. For example, if I consider D, at D the slope is positive and therefore F is negative, and that implies that the force is attractive at that point. Let us now consider another point, that is point B. Here again the potential energy curve tells us that the force is 0. Now this also corresponds to equilibrium, but this is actually unstable equilibrium position. Why unstable? Because in the first case potential energy is minimum, while in this case potential energy is not minimum, in fact it is maximum. So this A and B correspond to equilibrium position. One of them is stable and the other is unstable. Let's assume that this curve is drawn like this. Let's assume that subsequently the curve is here, and I'll consider one more point. This is point H. Now at point H, you notice that the potential energy remains constant. Even if I displace the object, the potential energy remains constant around that point. And that actually corresponds to du by dx is equal to 0, and d square u by dx square is also 0. And this is what is known as neutral equilibrium position. Neutral equilibrium position. So we can analyze the equilibrium by considering these details. Potential energy curve helps us in analyzing the equilibrium of a particle. Okay. One of the very important applications of what we have learned just now is the idea of what is called as work energy theorem. Work energy theorem. According to work energy theorem, the net work done by the forces acting on a particle is equal to change in the kinetic energy of the particle. Very simple. Net work done is equal to change in the kinetic energy of the particle by the forces acting on a particle is equal to the change in the kinetic energy of the particle. So we can write it like this: work done is equal to change in the kinetic energy, which is final kinetic energy, minus initial kinetic energy, which is half mvf square minus half mvi square. So net work done is given by this one. Now this assumes that the work is done by all the forces. Now if I consider conservation of mechanical energy, let's look at this one. This is actually quite useful as far as the problems in mechanics are concerned. Conservation of mechanical energy. Let's see what is that. If only conservative forces are acting on the system, then total kinetic energy plus potential energy remains constant. Total kinetic energy and potential energy remains constant. What does that mean? It means that work done by the mechanical forces, or say work done is, we can write it like this, that work done by mechanical forces, we can relate it to potential energy, or we can say the kinetic energy plus potential energy remains constant only if mechanical, rather conservative mechanical forces do some amount of work on the system. We can actually write it like this: for internal forces and for external forces, we can write it like this: net work done is equal to external work done plus work done by the internal forces is equal to 0, or work done by internal forces. External work done would be 0, internal work done is minus delta U, or minus delta U is equal to change in kinetic energy. So, this leads us to the idea that change in kinetic energy plus change in potential energy is 0, or kinetic energy plus potential energy remains constant. This is the idea of the conservation of mechanical energy. So, according to conservation of mechanical energy, total kinetic energy plus potential energy remains constant in the absence of any non-conservative forces. This is called as law of conservation of mechanical energy. So, let me repeat it one more time. In the presence of conservative forces, the sum of kinetic and potential energies at any point remains constant throughout the motion. This is known as law of conservation of mechanical energy. For example, we can consider a couple of cases here. If I consider, say, a freely falling body. In the case of a freely falling body, the body has the same total energy regardless of its position. Here it is only potential energy, it is dropped, assume that it is dropped. So, it is potential energy, while just at the point of contact, point of strike, it is just kinetic energy, while in between it is some potential energy plus some kinetic energy. Or if I consider, say, a pendulum. An oscillating pendulum, it is released from, say, the extreme position, assume. So, here it is just the potential energy and there is no question of kinetic energy becomes 0. And if I take this as the reference point, the potential energy here becomes 0 and the kinetic energy becomes maximum. And when it goes to the other side, same story, potential energy is maximum here and the kinetic energy becomes 0. And if I consider an intermediate position here, it possesses both kinetic energy and potential energy. It possesses both kinetic energy and potential energy. Law of conservation of energy. Understand the distinction between those two. The first one is mechanical energy, where only conservative forces are acting, and this time I am considering the presence of all the forces. If I consider the presence of all the forces, then how to represent this one? Let us look at it. According to this law of conservation of energy, if some non-conservative forces like friction is also acting on the system, the total mechanical energy is not conserved. It actually changes by the amount of work done by the non-conservative forces. So, we can put it like this: change in kinetic energy plus potential energy is equal to work done by non-conservative forces. It changes by the amount of work done by the non-conservative forces. So, this W, NCF is the work done by the non-conservative forces against the non-conservative forces. For example, the lost energy probably gets converted into heat or probably in the form of sound, etc. So, when non-conservative forces are present, the total energy remains conserved, which means that we can state it in a slightly different form. The total energy remains conserved can also be stated as the energy can be transformed from one form to the other, keeping the total energy constant. Remember this important concept. Change in kinetic energy plus change in potential energy is equal to work done by non-conservative forces. Work done by non-conservative forces. The idea of power is quite useful in handling a couple of problems here. Simple idea. This is nothing but rate of doing work. Rate of doing work is known as power. It's a scalar quantity and this is defined as dW divided by dt, or this is also written as the rate at which energy is dissipated. This is of course represented in terms of watt, W being the symbol. This can also be represented like this. If an object is moving under the influence of a force which makes it move at a velocity v, then the instantaneous power is given by F dot v. For example, I am making this move at a force F, instantaneous velocity being v, then the force is given by, or the power is given by F dot v. This can be written like this: Fv cos theta, theta being the angle between the force vector and the velocity vector. Suppose I consider rotational motion, a similar equation can be written. This can be written as, tau into omega. So it can be written as tau into omega. In the case of rotational motion, we can write a similar equation. Tau into omega gives us the relation between torque and the angular velocity. There are some important applications here. For example, let us consider some key results here. Let us assume that a block of mass m is pulled along the smooth inclined plane with constant velocity v. Let us assume that there is an inclined plane and a block of mass m is pulled along the smooth inclined plane with constant velocity. So it is pulled such that velocity is constant. Then the power spent is equal to mg into sine theta into v. Remember, this is a smooth one. Suppose friction is also present. This is rough. This is smooth, of course. In this case, the power spent is equal to mg sine theta plus mu mg cos theta into v. So if a block is pulled on a smooth horizontal surface or say inclined plane, power spent is this much, while on a rough inclined surface, this is the power spent. Suppose I consider a machine gun. Remember these results, of course. Let's consider a machine gun which fires n bullets per second, and each bullet is of mass m and it travels with velocity v. Then the power of the machine gun is equal to half m n v square. Then the power of the machine gun is half m n v square. Consider one more case. Let us consider a pipe from which water is coming out with velocity v, cross-sectional area being A, and it strikes a wall. Then the force exerted by the water on the wall, force exerted by the water on the wall is given by a v square rho. You have done it while doing laws of motion. And the power of the water is nothing but Fv, that becomes a v cube rho. And if the water reflects with the same velocity v after striking the surface, this is if it strikes the wall. If it returns with the same velocity, then I have F is equal to 2av square rho, and the power of this water is nothing but 2av cube into rho. So consider these two cases. Force exerted by the water on the wall is given by this expression, provided it does not rebound. In case it rebounds, then it is given by this expression. Now, in all these examples, remember in this chapter, most of the times we combine this idea with the idea of collision. That becomes very, very important. And of course, we also consider one another case, that is the case of vertical circular motion. So, the two important aspects of this particular chapter are vertical circular motion and the idea of collision. So, let us take up these two applications and let us look at some of the key results here. Vertical circular motion. A particle, for example, you can think of a simple pendulum. This is r, and let's assume that u is the velocity which is given at the bottommost point of the vertical circular motion. And a couple of points, this is A, this is a B, this is C, etc. These are some points. Now, a couple of important results are here. Number one, the condition to complete vertical circular motion, I will write as VCM, vertical circular motion is the initial velocity must be more than or equal to root of 5g into r. This follows from energy conservation, of course. From energy conservation, at A and at C you can get this result, and condition to complete vertical circular motion is u must be greater than or equal to root 5gr. Now, if u is equal to root of 5gr, it just completes vertical circular motion. In that case, the tension at C is equal to 0. The tension at C is equal to 0, and the tension at A is equal to 6 mg. Remember the results. If u is equal to root of 5gr, then the tension at C is equal to 0 and the tension at A is equal to 6 mg. And the velocity at B is equal to root of 3gr, and the velocity at C is equal to root of gr. So remember these results. If u is equal to root of 5gr, we have tension at C 0, tension at A is equal to 6 mg, and the velocity at B is this much, velocity at C is root of gr. Suppose I consider the same situation. This is A, and the journey happens from A to B, say. And this is a point under consideration, and at this point the forces are T and the resolved components are mg cos theta and you have mg sin theta, and during this journey, that means during the journey from A to B, the tension in the string is given by mg cos theta plus mv square divided by r. Mg cos theta plus mv square divided by r. That's right. So your mv square by r provides the necessary centripetal force. What is that equal to? T minus mg cos theta. And if I consider the journey from B to C, let me draw this diagram. This is B and this is C. This is theta, and clearly now this is mg sin theta and this is mg cos theta, and both t and mg cos theta are along the same direction. So for the journey from B to C, the tension in the string becomes mv square divided by r minus mg cos theta. So remember this result. Next one. In the same case, if the particle is to perform oscillations between A and B, that means it is to oscillate between A and B, that means it should function like a pendulum, then the speed must be less than or equal to root of 2gr. Remember, the velocity must be less than or equal to root of 2gr, that is between A and B. But remember, velocity can be 0, velocity is possibly 0, but the tension is not 0 between A and B. In A and B, it cannot become 0, because tension is given by mg cos theta plus mv square divided by r. So tension can never become 0 between A and B. Suppose I consider one more case. This time the same thing. I want it to project from this point A such that this leaves the path. It leaves from the circular track. Then the velocity must be in the following range. It must be more than root 2gr and it must be less than root of 5gr. So remember, if the velocity lies in this range, it obviously goes beyond point B, but it can't reach C. That's correct. It can overcome the point B, but it can't reach B. So what happens is that before it reaches C, the tension becomes 0. So in the range B to C, the tension becomes 0 before it reaches C. So at some point, say E, the tension becomes 0, the velocity is still present, the velocity is not 0. So what happens? The particle loses its circular track. The particle loses its circular track. It crosses the point B, but it doesn't complete the vertical circle. And when the tension becomes 0, the particle loses its circular track. Now, how to find out that at what angle, at what theta does it lose circular track? It is given by the following equation. Remember, cos theta is equal to u square minus 2gr divided by 3gr, and theta is measured from the vertical line, of course. So remember this result. Theta can be found out, that means the angle at which it loses the vertical circle is given by cos theta is equal to u square minus 2gr divided by 3gr. So depending on the value of u, you can find it out. And after leaving the circle, the particle will actually follow a parabolic path, isn't it? Simple. Because once it leaves, for example here, let's assume that it is this point at which it loses circular track. What happens? It is now like a projectile. So it follows a parabolic path starting from this point. So it follows a parabolic path. So remember this important idea, the idea of vertical circular motion. The idea of collisions. So what is a collision? In which collision is an event in which a large force, a relatively large force, acts on each colliding particle for a relatively short time. They come in contact with each other. But remember, it is not necessary that they are in contact with each other physically. For example, if I consider two protons which are shot towards each other, then separation between them becomes minimum for a particular instant, and this is also treated as collision. This can also be treated as collision. So just keep in mind. So in collision, the particles come closer before collision, and after collision, they either stick together or they move away from each other. They move away from each other. Now, the collisions, in collisions, one basic idea that holds good is conservation of linear momentum. Conservation of linear momentum is always applicable in the case of collisions. Whether kinetic energy conservation is applicable or not depends on the type of the collision. So, keeping this in mind, we have different types of collisions. One is based on the direction of collision. So, on the basis of direction, we have different types of collisions. What are those? Let us look at them. We have what is known as one-dimensional collision, also known as head-on collision. 2D, two-dimensional collision, known as oblique collision. What is 1D collision? The colliding particles before and after the collision travel along the same straight line. The particles move along the same straight line. For example, let us consider this is moving along this line, and the second which was moving along this line, and post collision this continues to move along the same straight line, and the second also continues to move along the same straight line. So this is pre-collision, this is post-collision. This is what is known as head-on collision, 1D or head-on collision. Now, in the case of oblique collision, let's assume that it's moving along this direction and it's going to collide with one more like this, and this was moving along this direction, and post collision it moves along this direction and the second one moves perhaps along this direction. This is what is known as oblique collision. Oblique collision. So you may notice that in order that the collision is head on, the velocities must be along the line joining their centers. This is a requirement for the collision to be head-on. Collision is head-on if their velocities are along the line joining their centers before and after the collision. Before and after the collision. So, based on the direction of collision or direction of motion, we have head-on and we have oblique. Based on another criteria. What is that other criteria? Based on the kinetic energy, we have elastic and we have inelastic and we have perfectly inelastic. So, elastic collision, inelastic collision and perfectly inelastic collision. So, now in the case of elastic collision, kinetic energy is conserved. Kinetic energy is conserved in the case of elastic collision. Total kinetic energy before and after the collision is same. So, you can see kinetic energy initial is equal to kinetic energy final. In the case of inelastic collision, some kinetic energy is lost. Some kinetic energy is lost, but the particles continue to move. Loss in kinetic energy takes place. In the case of perfectly inelastic collision, what happens is the particles stick to each other and they move. The particles stick to each other, the colliding particles stick to each other or they move with the same velocity after the collision. For example, collision between a bullet and a block of wood into which it is fired. This is an example for colliding particles sticking to each other. So, this is the example for perfectly inelastic collision. So, what are the two types of collisions we have? We have based on the direction and the second is based on the idea of kinetic energy conservation. So, how to or what are all the types here? The types are like this. Number one, we have head-on collision, we have oblique collision. So, let me write it. Based on the direction, head-on and oblique. Based on kinetic energy, we have elastic, we have inelastic and we have perfectly inelastic. So, these are the types of collisions. Suppose I consider one particular example in which elastic collision takes place in one dimension, that is head-on. We have a particle of mass m1 which is moving with velocity u1 and it is heading towards another particle of mass m2 which is actually moving with velocity u2. This is pre-collision, and post-collision this particle of mass m1 moves with final velocity v1 and the other moves with velocity v2. So, these are the parameters. This is the pre-collision, this is the post-collision scenario. Then the two key ideas remember are conservation of momentum How to write it? Simple. m1u1 plus m2u2 is equal to m1v1 plus m2v2. And conservation of kinetic energy. How do we write it? Half m1u1 square plus half m2u2 square is equal to half m1v1 square plus half m2v2 square. That is the kinetic energy conservation. Now, if we do these two things, we can obtain the expression for final velocity of the colliding particles. I am writing the result directly. This turns out to be m1 minus m2 into u1 divided by m1 plus m2 plus 2m2 divided by m1 plus m2 into u2. m1 minus m2 into u1 plus 2m2 into u2 whole divided by m1 plus m2. Likewise, v2 is given by 2m1 u1 divided by m1 plus m2 plus m2 minus m1 into u1, that is u2, divided by m1 plus m2. So, remember these results. If the collision taking place is elastic and head-on, these are the post-collision velocities. There are some special cases here. For example, m1 and m2 are equal and u1 is u, u1 and u2 are given by this one. Then what happens? Then we will have v1 is equal to u2 and v2 is equal to u1. The final result turns out to be v1 is equal to u2 and v2 is equal to u1, which means when two bodies of equal masses collide head-on elastically, their velocities are mutually interchanged. For example, as an extension, we can consider this one. If u2 is equal to 0 and u1 is u, then you notice that v1 is equal to 0 and v2 is equal to, what is it? u1. Which means that if two equally massive particles collide, one being moving and the other at rest, then their velocities get interchanged. The one which was moving comes to rest and the one which was stationary starts moving with the same velocity. Let us consider one more case. If the target mass is heavy, that means m2 is much greater than m1, then we will have v1 is equal to minus u1 plus 2u2 and v2 is equal to u2. If the massive target is moving slowly or it is at rest, that means if u2 is equal to 0, then we have v1 is equal to minus u1 and v2 is also equal to 0. That means when a light particle collides head-on elastically with a very heavy object at rest, the light particle recoils with the same speed and the target particle remains at rest. The target particle remains at rest. Another case. Suppose m1 is much greater than m2. Then we have v1 is equal to u1 and v2 is equal to 2u1 minus u2. And suppose as a special case, if I consider target particle is at rest, that means u2 is equal to 0, then v1 is equal to u1 and v2 is equal to 2u1. An interesting case. If a heavy particle strikes a very light particle initially at rest, then the heavy particle continues to move with the same velocity, while the light target particle moves with the velocity twice that of the heavier particle. Okay. Now, how to deal with inelastic collisions? Now, inelastic collisions are understood in terms of something known as coefficient of restitution. Coefficient of restitution. This is a concept which is useful in handling inelastic collision. This coefficient of restitution is defined as velocity of separation along line of impact divided by velocity of approach along line of impact. That is nothing but V2 minus V1 divided by U1 minus U2. V2 minus V1 divided by U1 minus U2. Now, for a perfectly elastic collision E is equal to 1, while for a perfectly inelastic collision E is equal to 0. So, we can say E lies between these two values, and in general for inelastic collision the value of E lies between these two values. So, we can generalize it like this. Suppose we have head-on inelastic collision. This is U1, M1 and M2, U2, and post collision we have M1, V1 and M2, V2 respectively. Then again momentum conservation is applicable, kinetic energy is not conserved, and we can use the expression meant for coefficient of restitution, and if we find the equations or if we write the equation solve, we get V1 is equal to M1 minus EM2 into U1 divided by M1 plus M2 plus 1 plus E into M2 into U2 divided by M1 plus M2. This is the final velocity considering inelastic collision. Final velocity of the second particle is M2 minus EM1 into U1 divided by M1 plus M2 plus 1 plus E into M1 into U1 divided by M1 plus M2. This is U2, M1 plus M2. So, these are the post collision velocities considering the inelastic collision. Remember these values. These equations are not so easy to remember. So, you have to write it a couple of times and then get the answer. Suppose I consider such an inelastic collision. In the case of inelastic collision, there is a loss in kinetic energy, and that loss in kinetic energy is given by M1 M2 divided by 2 M1 plus M2 into 1 minus E whole square into U1 minus U2 whole square. U1 minus U2 whole square. So, remember this one. In the case of inelastic collision, the loss in kinetic energy is given by this expression. That is m1 m2 divided by 2 times m1 plus m2 into u1 minus u2 whole square 1 minus c square. Right? Remember this expression. Suppose I consider elastic collision. The total kinetic energy is conserved, you know that. Total kinetic energy is conserved. However, individual particles don't retain their kinetic energy. That's right. So now the kinetic energy of one and the kinetic energy of the two can be found out. Now, suppose I concentrate on the first particle in our earlier example, then its final kinetic energy can be calculated, you know, its initial kinetic energy being given by half m1 u1 square, and the final kinetic energy can be written as m1 minus m2 divided by m1 plus m2 whole square into initial kinetic energy. So I can write kf divided by ki is equal to m1 minus m2 divided by m1 plus m2 whole square, and the fractional change in kinetic energy, that is nothing but ki minus kf divided by ki, can be calculated, and it turns out to be 4 m1 m2 divided by m1 plus m2 whole square. I expect you to remember these results. I expect you to memorize these results as far as the change in kinetic energy is concerned, the fractional loss, etc. Because these are the equations which are worth remembering. You have to write these equations a couple of times to get good flow. Okay, so with these concepts and equations, we have come to the end of this discussion. In our next session, we will take up numerical problems based on the concepts that we have learned here. All the best. Thank you very much.